My name is Robert Close, and today I'll be giving you some simple calculations of classical spin angular momentum. Spin angular momentum is just ordinary angular momentum. You can think of it as the effort or torque multiplied by time required to stop rotation of an inertial substance. It is the conjugate momentum to angular velocity, and unlike the usual expression for angular momentum, it's independent of the coordinates. So fundamentally, motion can be separated into two types. There's irrotational motion that has zero curl, and incompressible motion or rotational motion that has zero divergence. And you can take any vector field, in this case momentum density, and decompose it into a constant plus a gradient, which has zero curl, plus a curl, which has zero divergence. And for incompressible motion, in the rest frame where this average momentum density is zero, the momentum density just reduces to a single curl, where this S vector field is what we call spin density, and it represents angular momentum. So spin density is the vector field whose curl is equal to twice the incompressible momentum density. And this relationship is valid both in classical physics and in quantum physics. And just to give a connection between quantum and classical physics, if you take the equation for an electron, the Dirac equation, multiply by the conjugate wave function times the Dirac matrix, sigma I, add the adjoint, and you get this equation. And if you combine terms, from the adjoint with the other term, you can write that in this form. And if you multiply by h bar over 2, then this term in here would represent the spin density. And it turns out these terms just correspond exactly to terms in the ordinary wave equation. So with spin density being a time derivative of vector potential q, this becomes the second derivative of q, and with a factor of 2 tossed in there. This gradient term actually becomes the gradient of a divergence of q for this term. And the last term ends up being the double curl of q. So these last two terms combined give you Laplacian. And the factor of c squared there is just to get the units right. Okay. So elastic waves have two types of momentum and angular momentum. There's the wave momentum associated with propagation, also called dynamic momentum. And then there's the conjugate or intrinsic momentum, which is due to the actual motion of the material. And likewise, there's two types of angular momentum. There's the wave or orbital angular momentum, and then there's also the spin or intrinsic angular momentum. And these intrinsic or conjugate momenta imply the existence of some kind of inertial substance. And we can think of the vacuum as having material inertia, or we can just call it an ether, which is the old term for that. And we can compare that with the equation for a wave on a string, for example, with the mass per unit length ρ1, displacement perpendicular to the length of the string, c, and a tension t. This just says that the mass times acceleration is equal to the force. And if we look at the momentum per unit length, there's a wave contribution associated with the wave propagation, and then there's an intrinsic momentum associated with the actual motion of the string up and down. Okay, so this is in one dimension, and when I talk about spin density, that's in 3 dimensions. Okay, so just a caution to get the terminology straight. The spin density is classical angular momentum density. Okay, it's what we think of as rotation of an inertial substance. But quantum mechanical motion of material objects is wave motion. So when matter actually is moving through the vacuum, that's a wave motion. So what we normally call rotation of an inertial substance is actually the wave or orbital angular momentum. Okay, so when I refer to classical spin density, I'm referring to a property of the vacuum or ether in classical physics as an interpretation of relativistic quantum mechanics. Okay, so there's 2 types of momentum, the intrinsic and wave momenta. There's 2 types of angular momentum, the spin and the orbital. The orbital angular momentum is associated with the potential energy and the torque and wave propagation, whereas the intrinsic spin and intrinsic momentum are the ordinary momentum and angular momentum that we associate with moving substances. Okay, but objects propagate through space as waves, so what we observe is wave momenta. Okay, the relationship between spin density and velocity and angular velocity is similar to the relationship between the magnetostatic vector potential, the magnetic field, and the current. Okay, so there's a close analogy there mathematically. Okay, if we look at integrals, usually if we want to calculate total angular momentum, we would calculate r cross p and then integrate. But if we substitute this expression for p into the integral and do some integration by parts, we would find that that integral is the same as just integrating the spin density directly, plus some boundary terms, maybe at infinity, that we can just assume to be 0. And if we calculate kinetic energy, 1/2 rho u squared, integrate that, again, we can integrate by parts, and in that case, we get the angular velocity times the spin density, which is similar with the kind of calculation we normally do with angular momentum. Okay, if we have a Lagrangian that depends on the velocity only through the kinetic energy, the normal way, then the spin density would be the momentum conjugate to the angular velocity. So if we start with 1/2 rho u squared, we can integrate that by parts. We get w dot s, angular velocity times the spin density. And doing the functional derivative, we have to treat s as a function of the angular velocity as well. Just like here, there's 2 factors of u. Here, we're going to end up getting 2 contributions here. So the factor of 2 drops out, and the conjugate momentum is the spin density. And likewise, the momentum density is the momentum conjugate to the normal velocity. Okay, so for incompressible motion, as we said, the spin density, actually the velocity and angular velocity have similar relationship as the magnetostatic, vector potential, magnetic field, and current. Okay, the difference is we don't normally calculate the total integrated vector potential, but we do calculate the total angular momentum. Okay, so let's look at an example of just a rotating cylinder, very simple example. And the spin density in that case is parabolic, maximum at the center and drops to 0 at the edge. If we take 1 over 2 rho times the curl, we get we get a velocity in the azimuthal direction, r times the angular velocity. And if we take half the curl of that to get the angular velocity itself, it comes out to be a constant inside the cylinder, and then there's a delta function at the edge where the velocity suddenly drops to 0. So velocity is increasing outward and then suddenly drops to 0. So we get a delta function with a minus sign at the edge. Okay, and if we integrate that, the volume element is going to be the height times 2 pi times r dr. So we're going to get r fourth over 2 on this term, and we're going to get r fourth over 4 for this term. So the difference is going to be r fourth over 4. We can factor out a pi r squared times the height times the density to get the mass. So this ends up being mr squared over 2, which is the normal moment of inertia, and then multiplied by the angular velocity. So we get the normal expression for angular momentum of a rotating cylinder, and also the same kinetic energy, because with the constant angular velocity, you're just multiplying 1/2 times W0 here. So we get the same kinetic energy as well. Okay, a little more complicated example is a annular ring rotating. So between the inner and outer radius, it's the same as for the complete cylinder. But on the inside, the spin density is just constant, so that the curl inside is 0, no velocity. So when we do calculate the velocity, between the inner and outer radius, it's the same as for the cylinder. And angular velocity also between the inner and outer radius is same for the cylinder. There's also delta functions at the edges, but I'll just ignore those. Okay, so when we do the integral, this time we're going to get a difference between the outer radius to the 4th minus the inner radius to the 4th. And when we factor out the mass, which has a factor of r2 squared minus r1 squared, we're left with the mass times r2 squared plus r1 squared over 2. So again, multiplying that by the mass, that gives the correct moment of inertia. So we get the normal expression for angular momentum, and also the usual expression for kinetic energy. Okay, and you can note quickly if this inner radius goes to 0, we recover the complete cylinder. Okay, I'll just do one more example. In this case, the cylinder is not rotating, but just moving along the z-axis. So in that case, the spin density is going to be 0 everywhere, because you just have, sorry, not 0 everywhere. The spin density is going to be radial inside, but it's going to point in the azimuthal direction. So on the inside, you have to have a constant curl, so it's proportional to r. And on the outside, you have 0 curl, so it turns out that's 1 over r. All right, so then calculating the velocity inside the cylinder there, 1 over 2 rho, and then it's 1 over r ddr rs phi. That gives you the correct velocity, uz. along the z direction. It's constant. And angular velocity is 0 inside, and then there's a delta function at the edge where the velocity coming in goes from 0 to uz. Okay, so in this case, because the spin densities in the azimuthal direction, when you do an integral, it's going to integrate to 0. But the kinetic energy, if you plug in the delta function for angular velocity and multiply that by the spin density at the edge, at the radius here, and then integrate, what you get is 2 factors of uz, so you get uz squared, and then the integral of the volume over the delta function works out to be multiplying by the mass. So you end up with 1/2 mass times velocity squared, just like you would expect. Okay, so in summary, the spin angular momentum is just the ordinary angular momentum in coordinate independent form. It represents the effort, which is torque times time, required to stop rotation of an inertial substance. It's related to the moment of momentum through integration by parts. It is the conjugate momentum to angular velocity. And there's an analogy with magnetostatics, where the spin density, velocity, and angular velocity have this similar relations as the magnetostatic vector potential, the magnetic field, and the current. Okay, thank you for your attention.